In this video, we're going to be talking about inverse functions. So what are inverse functions? How can we recognize them numerically, graphically, and algebraically? We'll try all three. First of all, let's define an inverse function. An inverse function, in its most basic way, are two functions where their inputs and outputs get swapped or exchanged. So we'll see some examples down here when we get into that. But essentially, the domain of one function is the range of its inverse and vice versa. The range of one function is the domain of its inverse. More importantly, inverse functions will undo or cancel each other. And so you're kind of familiar in working with inverse functions already. Whether or not you knew it, multiplication and division are inverse operations, so they will cancel each other. We know that exponents and their corresponding roots, for example, if I had x squared, the square root of x would cancel that. Any exponent and its corresponding root will cancel, so those are inverse functions. If you know a little bit about exponential functions or log functions, then maybe you know that those are inverse functions and they cancel each other. We'll do more of that definitely in this class a little bit later on. And I hope you've had experience dealing with trig functions in geometry or maybe algebra 2, where if you need to find the unknown side length of a right triangle, you can use sine, cosine, or tangent. If you wanted to solve for the unknown angle measure, however, you would use the inverse sine, inverse cosine, or inverse tangent. And as it turns out, those two things cancel each other. Inverse sine would cancel sine. We'll do more of that in the second semester. Eventually, if you get to calculus, this becomes a really big concept where the two main themes in calculus, derivatives and integrals, are actually inverse functions, and they will cancel each other. So you'll play around with that concept a whole lot in a calculus class. So inverse functions are a giant concept in math, and they just get more and more important as you go. The inverse notation, how we notate an inverse function, is by putting a little -1 next to its function name. I know that that looks like it's an exponent, but if it's next to a function name, we read that as the inverse of f, or the inverse of function f. If you see that -1 next to a number or a term, well then that is the exponent version of it, which is just a reciprocal. But next to a function's name, that means inverse function. All right, let's do it numerically. How can we identify inverse functions by looking at a data table or their coordinates? Well, we can tell that they're inverse functions if the input becomes the output for the inverse, or the output becomes the input for the inverse. It's a tongue twister. Notice that any number that I plug in, I'll get an output here for this function f. But then if I were to plug that output back into its inverse, it will give me back the original input. This is where a big misconception about inverse functions usually happens here with the notation. Notice that we have a function x plus 4, and we also have an inverse function also saying x minus 4. Well, these two x's are not the same thing. Even though we use an x to symbolize the input, we really should be thinking like for an inverse function, I'm plugging an output in, and that can get pretty tricky to think about. So even though we use x, we should think y. For example, if I were to plug 1 into my original function f here, I get 1 plus 4, that's 5. If I had a misconception about what this x was, maybe I would plug that x value into this one and try 1 minus 4, but then I don't get 1 out of it, and I don't see that inverse relationship happening. So what we have to instead do is remember that even though it's an input variable being used to symbolize our input spot, really what we're plugging in is the output of our original function. So if we go ahead and plug the 5 in, 5 minus 4 is 1, and so now we can see that inverse relationship happening. So I'll try and continue to emphasize that throughout the video here. All right, two things we're about to do. One is, given an inverse function, given an original function, can we find its inverse? We're going to do that algebraically. And then we're going to use what's called a verify step. We're going to have a two-column proof, essentially. It's just separated by a column here, where we can plug one function into the other and prove that we get a common result. So let's see what we get here. Anytime you want to verify that two functions are inverses of each other, you can plug one into the other. You can plug the inverse into the original function. That's what this notation is saying. Notice that the inverse is the input, or inside, getting plugged into the original f function. So up top, the inverse was x minus 4. If I take that whole expression and I plug it into the input for my original equation, then I get x minus 4 plus 4 is still left over. And the 4's will cancel, we're left with x. So that's a good sign. Anytime you plug one inverse function into its original, or vice versa, you should always get x as the simplified result. Let's try it backwards. Here we did the inverse plugged into the original. Let's flip that around and plug the original into the inverse. So there's our symbol there. So take our original function, x plus 4, and plug it into the input for the inverse. So now we have x plus 4 minus 4. And if we simplify that, we get an output of x. And that's what we wanted. So if we do that both ways, and both times we get x out of it, we verified that those two functions are inverses of each other. So that's the algebraic way to prove inverse functions. Use that composite. All right, so a couple examples doing those two steps here. First, we're going to find the inverse function of 4x, and then we're going to use this composite method to verify that we were correct. One thing you can do is change f of x to y. So instead of f of x equals 4x, you can say y equals 4x. And normally we solve equations for y. The inverse of that would be to solve for x. So we could just solve our equation for x to get the inverse function. So instead of multiplying by 4, we're going to divide by 4. So we get x is y over 4. That would be the inverse function, but we have to change the notation a little bit. This is just standard notation. Instead of x now, we're going to say that that's the inverse. So f with that -1 of x, that's the inverse function of f. So we've replaced that x right there with that notation. And then over here, instead of y divided by 4, even though that's what we need to keep in our head, the notation is going to make us rewrite that y into an input variable x instead. And so again, just to double check our understanding here so that we don't make a mistake in the future. For example, if I wanted to plug a 2 into my original function, so I plug a 2 in here, 4 times 2 is 8. I know I have a coordinate on that graph, 2, 8. If I tried to plug 2 back in here, 2 divided by 4 would be 1/2. I would not see that inverse relationship happening. So you have to think, I'm really plugging the output back in to check it. So if I plug an 8 in instead, then 8 divided by 4 is 2, and 8, 2 would be a point on the inverse graph. All right, so we found our inverse function. We did try to prove it using a coordinate, but let's just use that composition just to really prove our point. If I plug the inverse into the original, meaning if I plug x divided by 4 into 4x, I get 4 times x divided by 4. And the 4's will cancel, becoming 1 and leaving x behind. Do it the other way. Always do it both ways. This time I'm going to plug the original function into the inverse. So I'm going to take my original 4x and plug it into x divided by 4. So now I have 4x divided by 4. And again, the 4's cancel, and we're left with that x. It really doesn't matter which one of these you do first, as long as you do both of them and guarantee that you get x out of both of them. If that happens, then we know that we were correct in coming up with the inverse function. One more time. You can pause the video, try it out on your own, or just follow along right now. Given our function x minus 6, what's the inverse function? Well, we could think, how do we undo subtract 6? We're going to add 6. Let's see if that's what we get. taking our original function, x minus 6, changing the f of x to y if you need to. Instead, writing y equals x minus 6. We're going to solve for x instead, add 6 to both sides. So now, in terms of y, we have our inverse function, y plus 6. But let's rewrite it using that function notation. Instead of x, change it to the inverse function notation. Instead of our y, change it to that input variable. But remember, we really mean we're plugging the output back in if we needed to. So now we have the inverse function is x plus 6. Let's verify by using our composition here. Plug the inverse into the original. So let's plug x plus 6 into this x spot. So we have x plus 6 minus 6. 6 is canceled, we're left with x. So the inverse functions are canceling each other's operations. Same thing over here, but backwards of what we just did. Plug the original into the inverse. So let's take x minus 6 and plug it in x plus 6. So we have x minus 6 plus 6. 6 is canceled again, we're left with that x. We just verified that those are two inverse functions using composition. So that's algebraically proving it. One more thing we got to do is talk about it graphically. So we'll discover this rule right here by taking a look at these two functions here. These are inverse functions. I can see x to the 5th, and I can see the 5th root of x. But let's see what it looks like graphically. So if we graph those two things, we should end up seeing some symmetry here. I'll let you do that on your calculator. What you should recognize is that x to the 5th and the 5th root of x are symmetrical across this diagonal line. And that diagonal line is represented by y equals x. And that's true of all inverse functions. No matter what they are, if they're inverses, their graphs will always reflect across that diagonal line. So if you see a question with just graphs on it, and you're asked whether or not they are inverse functions, you're looking for that symmetry across that diagonal y equals x line. All right, the last thing, which is probably a good starting point to circle back around on. Wouldn't it be nice if we could prove that a function has an inverse before we try and find its inverse and prove it? Well, of course, that would be the best starting point. So in order to first of all prove that an inverse function exists, we have to establish if it's a one-to-one function. The definition says that if a function is a one-to-one function, then it will have an inverse function. If it's not in a one-to-one function, then it won't have an inverse. Well, that's not entirely true. We'll see on our last example what we can do in that case. But for now, we're going to check to see if a function is one-to-one, and if it is, then we'll be able to find its inverse. So a one-to-one function is a function where each input has a distinctly new output, meaning that there are no inputs that share an output. For example, here on the left, this is a function. It does pass the vertical line test. It's okay if different inputs give the same output, but that's not a one-to-one function. I would need to have totally separate new outputs for each of my inputs if it was one-to-one. So what we can do as a quick test is just draw horizontal lines. So we can test functions by drawing vertical lines. We can test to see if they're one-to-one by drawing horizontal lines. Notice if you draw a horizontal line through a lot of places on this graph, you hit more than one of the same output. So it doesn't pass the horizontal line test. It's not one-to-one. This graph, however, if we draw our horizontal lines, even at that spot right there where it looks a little close, you may have to zoom in sometimes to really test it. But that is only going to hit our graph one time for every horizontal line drawn. So that's a one-to-one function. I can find its inverse or I can draw its inverse. So use the horizontal line test to first determine if a graph has an inverse, or if you're given the equation for a function, graph it and do that. Sometimes, though, there are equations that I hope we remember the parent graphs of. And so if you can visualize that graph instead of using a graphing utility to do it, it's a little faster. For example, the square root function always just blasts off from an endpoint. That will always pass our horizontal line test. So that could be, or that has the potential to have an inverse function. Absolute value functions, though, always use that V shape. And so if I draw a horizontal line, it's not going to pass that horizontal line test. So inverse functions are not going to have, absolute value functions are not going to have inverse functions necessarily. Lastly, just another example here. We got a cube root. It's our disco graph. Passing the horizontal line test? I think it does. So again, if you just know that parent function form and you know things about transformations, then sometimes you don't necessarily have to graph it. But if you don't remember those, then it's probably a good idea to look at the graph on a graphing calculator if you need to and visualize that horizontal line test. All right, as I was hinting, there are some functions that are not one-to-one, but we can do a little trick to it. We can actually restrict the domain and just look at a portion of the graph or a portion of our function, and we can have portions of functions that can have inverses. That's a little weird. For example, x squared is a parabola here. It doesn't pass the horizontal line test. It's not a one-to-one function. It is a function, but it's just not one-to-one. What we can do is we can just ignore half of the graph. What if I just want to focus on the right side of that parabola? That would be using x values that are greater than or equal to 0. And now I have a graph that does pass the horizontal line test. And so I can find its inverse function. So instead of f of x equals x squared, let's change that f of x to y equals x squared. Let's solve for x, square root both sides, and we got our inverse function. Now the square root of y in our function notation goes back to the square root of x, though. That's our inverse that we're talking about. And now we got to restrict that domain, which was the range of our original function. So if we go back to our original function, its range was y values that are greater than or equal to 0. So now that becomes the domain of our inverse function. But you could also think about the square root of x, knowing that that is typically the domain. So there's one way that you can take a function that's not one-to-one. You can instead restrict its domain and talk about the inverse of just part of that function. All right, so there's a lot about inverse functions there. Can you think about them numerically? What happens to their data sets? Can you think about them algebraically? Can you find inverse functions by solving for x and use that composition to prove? And lastly, can you think about inverse functions in their graph form and use that horizontal line test to determine if it's a one-to-one function so that you know it has an inverse? Or can you look at that symmetry that we talked about right here, that symmetry across the line y equals x? So practice your inverse functions.